Module 21 Gaussian, Log-Normal, Binomial and Poisson Distributions. Section 1 Continuous Probability Distributions, Gaussian and Log-Normal Distributions. Probability distributions are these are the descriptions of the random phenomenon in terms of probabilities of an event. So events that are occurring randomly, so then they are expected to be part of some non-distribution. So if the event is non-random, then the probability distribution doesn't make much sense. So it is for the random events. So probability distributions are rarely useful in biology. That is what you should know that. So these distribution based calculations are mostly, it's not much of the use in the biological science, except in some rare occasions, because it follows a deductive logic. It starts with a non-probability for the population and computes chance of observing various outcomes in the random sample. So in most of the cases, the probability of that population is not known. So we are actually interested to calculate what is the probability in that. So for example, how much is the probability of the incidence rate of the AIDS in Indian society is so that is that we are calculating. So if we know it, the reverse option is what this probability approach is all about. So in experimental biology, we don't know the population. We usually work with the samples to infer the estimates of the larger population. That is actually inductive logic. But in this case, it is a deductive logic, so it's not much useful. So there are several kinds of probability distribution. The types are either continuous distribution or it is discrete distribution. For the continuous distribution, the main methods are, the main distribution types are Gaussian or normal distribution, log-normal distribution, that these two things that we are going to introduce in this section. Others are T distribution, that we have already seen this T distribution in module number 16. F distribution, we learned it in module number 17, and chi-square distribution we learned already in module number 18. While in the case of discrete probability distribution for discrete variables that you can count on, so Poisson distribution and binomial distribution, that we are going to learn that in both of that in our next section. There are also negative binomial distribution as well as geometric distribution also that we are not covering in this course, but if you are interested, you can search it about. First is the Gaussian distribution. So it's very well known distribution. It's a bell-shaped distribution, and this is where the 3 sigma rule as originated. This distribution is followed when many random variables create the variability. So random factors tend to offset each other. So additive distributions of factors add up onto one another. So that is the reason for this bell-shaped curve. So if you look at the mean of the average is usually same as the population. The sample mean is usually same as the population mean. Sometimes the sample mean is lesser than the population mean, so you are getting a negative one, while sometimes the sample mean is going to be positive than the population mean, then you are going to get the positive. So if you plot the distribution, it's going to be more or less like a bell shape. So this is an additive distribution, so that is very important. This is log-normal distribution that we are going to discuss later is multiplicative, but this one is additive distribution. So there is another kind of distribution called standard normal distribution. So it's of course the Gaussian distribution, but this one is more standardized. So here the mu, that is the sample mean, is 0, while standard deviation is 1. That is when you are going to get the standard normal distribution. So we learned about this standard normal distribution in the module number 11S1 when we discussed about the confidence intervals. So any Gaussian distribution can be converted into the standard normal distribution by this formula. So the transformation formula is actually very simple. That is Z is equal to the sample mean, that is M, minus the population mean, that is mu, divided by sigma, the population standard deviation. So here you need to know the population mean, the exact population mean, to calculate this Z. So that is why if you don't know the population mean, then this formula makes no sense. But this is still useful if you are doing some simulative study. So Z is also, what is actually the real meaning of this Z? Z means number of standard deviations away from the mean. For example, Z is 2 means that the mean is 2 sigma or 2 standard deviation away from the mean towards the right, because it is positive. So it is towards the right. If had it been negative, it will be towards the left. So the 3 sigma rule is also very clear. That means that almost 95% of the values fall within 2 standard deviations of the mean. Almost 98.6% of the whole value falls within 3 standard deviations of the mean. So that's what is known as central limit theorem in statistics. So that is all from the central the standard normal distribution. So central limit theorem is the distribution means of the random sample will follow the Gaussian, even though the population from which the samples are drawn is non-Gaussian. So even though the population is non-Gaussian, the samples will follow the Gaussian distribution, and that is what the central limit theorem is. So approximately 2/3 of the values lies in 1 standard deviation of the mean, approximately 95% in the 2 standard deviation of the mean, and that is basically, it's not exactly 2 standard deviation of the mean, it is basically 1.96 is to be exact of the mean. So that is why this multiplier comes while calculating the confidence interval, if you remember that. So the normal distribution is that central, it's a general probability distribution for continuous random variables. So the formula of this normal distribution is given here, which is not too complicated to comprehend, but this formula is of rarely useful because we follow another approach. The approach is basically to calculate the z. So how do you actually calculate the probability from given an x? So first step here is to calculate the z. So what is z? Z is nothing but the sample mean minus population mean divided by standard deviation. So if you know all these things, you can calculate the z, and then you can look up the table, and then the standard normal distribution table, and then you can calculate or you can approximate the p-value. So standard normal z table is it has already been given in the course website. The PDF is downloadable. When you click on this slide, you can download that PDF. So it is basically standard normal distribution is, as I told you, here the mu is 0 while standard deviation is 1. So in this case, if you know z, you can calculate the p-value from this table. So basically z, if you know z, all you are doing is you're looking the z at 10th position in vertically, and then 100th position, that means the decimal point 0.01 onwards, you will be looking up horizontally, and then you can pick up this p-value from this table directly. One example is that average mark in the first sessional biostatistics test is 11, that is the average one, 11.03. So what is the probability of a student to get 4 marks at 0.05 significance level? So what is the probability that a student gets 4 marks? So first is to calculate z. So x minus mu upon sigma. So x is your score, so it could be either the sample mean. When you are actually approximating population mean to the sample mean, then it is actually the sample mean, that is m minus mu. So in this case, our thing is to calculate the probability of an event. So to calculate that x is being used. So in this formula, it is x minus mu divided by standard deviation. So here the x is already know, it is 4. To get the 4 marks, what is the probability? So 4 minus, so what is the average mark? So you have to substitute, so it is 11 marks. Now divided by what is that standard deviation? Standard deviation is 3, right? Because we already know that the standard deviation, because 11 plus or minus 3. So plus or minus 3 is standard deviation. So in that case, so we know the standard deviation as well. So if you plug into it, you are going to get 2.333 as z value. So if you know this is the value, then you can just go to the standard normal distribution table, and then 2.33, then 3. So to pick up this value, so the value is basically 0.00990, but remember this is one tail p-value. If you want to calculate 2 tail p-value, then you will have to multiply with 2 to get a p-value of 0.0198, because in distribution both sides make sense, right? unusual score could be either too high or too low. So that is why go with the two-tail probability. So the probability is 0.0198. So what is this? What is the conclusion of this one? The conclusion is that at 0.05 it is a significant score. So that means that it is basically an extraordinary score, either too low or too high. So that is the conclusion. So the conclusion is statistically significant. So you can also use an online calculator to do the same thing at this location that is already given here. That uses the standard normal distribution to calculate the exact probability of an event. But of course you have to know the sigma as well as the population mean. So if you know it, then you can do that to calculate probability of an event there. So at the Gaussian distribution, that is the central limit theorem. If you look at the central limit theorem, the way it is being explained to you earlier as well, at 95% confidence level, so maximum unusual is going to be 2 sigma, while minimum unusual is going to be, the mean minus 2 sigma. So mean plus 2 sigma and mean minus 2 sigma. 2 is again, it's a approximation. 1.96 is more accurate, but still it's a good guess 2. So given this, then how can you answer questions like this? Average mark in the first session of biostatistics is 11 plus or minus 3. Is it unusual at 95% CI for the student to get the following marks? 1 mark, 4 marks, 17 mark. Are these unusual? So it's actually very simple to see that is it usual or unusual, because as I already explained to you, 11 plus or minus 3. 3 is the standard deviation. So all you have to do is 11 minus 6, that means 3 multiplied by 2. 3 is the standard deviation, multiplied by 2 is 6. So 11 minus 6 to 11 plus 6. So in between that range, whatever the score is not unusual, but beyond that in both sides it is unusual. So you can use this logic and you can solve and discuss your answers in the discussion sections. Another question here is that human body temperature is normally distributed with a mean of 37 degrees Celsius and standard deviation of 0.8 degrees Celsius. Now the first question is that what is the probability that a random person has temperature which is lesser than 35 degrees Celsius, 35.1 degrees Celsius? Second question is, what is the probability that a random person has temperature more than 39.1 degrees Celsius? And the third is, what is the probability that a random person has temperature between 36.2 and 38.3 Celsius? So it is a range basically, So how do you solve it? It's actually pretty simple. First is, what is the probability that a random person has less than 35.2 degrees Celsius? So Z, you can calculate the Z. So the given is 35.2. So 35.2 minus the mu is 37 divided by the standard deviation, that is 0.8, which is going to be negative 2.25. So you can calculate this p-value by looking up in the table, or you can take up this online calculator which is given here, right here. So this calculator I recommend you, because this calculator will also give you the probability distribution function, that is a histogram, and to tell you exactly how much area is being used for that probability. So this probability is one-tail probability is 0.0122 is a one-tail probability. Here's one-tail probability is perfect because the question asks you to calculate lesser than 35.2. So definitely there is the direction is known. So in that case you can definitely go with the one-tail p-value. You don't have to calculate the two-tail p-value here. And remember that in the standard normal distribution, it's always cumulative. The probability value is always cumulative, that adds upon another, because that is basically the area up to that, the whole area is actually added on to it. So that is why these are all cumulative probability. Part 2 of our question is that what is the probability the random person has temperature above 39.2. So here it is basically the positive value you are going to get. So it's basically 2.75 is a Z score, and you can look up in the table, or you can put this value here. Then it will calculate you the p-value of 0.00298. That is the one-tail p-value. So both these p-values are pretty it is very low, 0.05 is a significance level. In that case, both are significant results. So the person getting a body temperature more than 39.2 or less than 35.2, both are outliers. So both are significant result. That is what this means, the interpretation of the p-value. Coming to the third part of the question, that is a little bit tricky. Here it is, what is the probability that a random person has temperature between 36.2 and 38.3. So see the two things, the two temperatures. So how to calculate that? So first of all, you have to calculate for lesser than 38.3. So that you can calculate normally. So if you calculate the probability, that is going to be 0.94792. So you can also calculate the probability for lesser than 36.2, that is 0.15866. Now between 36.2 and 38.3, that is just subtracted these two probability values. So you are going to get 0.78928. So see, the first one is the lesser than 38.3 means everything. You can see the upper panel, so all the sections that is being highlighted is lesser than 38 point, the 38.3 degrees Celsius. So here in this case, that also includes lesser than 36.2 also, right? So that part has to be subtracted, otherwise it's going to be trouble, because we have to calculate in between. So that is a region, that is you will see that in this diagram you can see two lines, the green line. So in between these green lines only we have to calculate the area. So to do that, first of all we have to calculate the whole area. Then we will also have to calculate the area to the left of the leftmost green line. Then that is basically the interspersed area. So that way you can calculate it, and the probability is now 0.78926. So that means 78% is the chance of getting that kind of temperature. So which is perfectly reasonable, because most of us have temperature between these two ranges. So that is perfectly fine. Another question is, IQ intelligence quotients are randomly distributed with mu is 100 and sigma is 15. So we know the population mean, and we also know the population standard deviation. What is the probability that a random person has IQ less than 115? What is the probability? You can calculate that using standard normal distribution equation. You can calculate Z, and then you can check up the p-value. What is the probability that a random person has IQ higher than 135? Again, that's very simple. What is the probability that a random person has IQ between 90 and 110? So lesser than 110 you can calculate the p-value, lesser than 90 you can calculate the p-value. So lesser than 100 minus lesser than 90 is going to be 90 and 110. So you can do this work and discuss the answers in the discussion column. So coming next is log normal distributions. So log normal distributions are multiplicative instead of additive. The Gaussian is basically additive, because this emerges when the variation is caused by multiple sources of scatter which add together in the case of Gaussian. In contrast, log normal distribution emerges when variation is caused by multiple sources of scatter which are multiplicative in nature. So that is the reason why this log normal distribution, this is how it looks like. On the left side is log normal distribution, which is which is quite skewed, while in the case of normal distribution is perfectly in the bell shape. And if you look at that in the column scatter plot, you will see that in the log normal distribution almost all the values are cluttered in one small group which is very near to the mean, while you will see that one or two values will be too further away. So if you see this kind of situation, chances are high, and if all the values are positive, chances are high that the distribution is log normal. It is not really normal distribution. The tendency is that we actually tend to pick up these values on the top as an outlier, and then we declare that the distribution is normal and perform the test appropriate for the normal distribution, which is wrong. So that is the issue with this log normal distribution. Now log normal distributions are very common in the biology as well as sciences. Some of the examples are milk production by the cow. So how the cows are producing the milk, or IC50 value, inhibitory concentration 50 value, or EC50 value, or drug or toxin plasma levels, or Km and Ki in the enzyme kinetics, or permeability and solute mobility in plant cuticles, or rate of constant desorption, and powdery mildew on barley, species abundance, amounts of rainfall, size distributions of the rainfall droplets, all follow the log normal distribution, which is quite common. So transformation of the normal distribution through exponentiation is very easy way to deal with this kind of situation. So asymmetrical or skewed distribution with low mean values, large variance, and all positive values often fits in this kind of distribution. Values must be positive, as log of x is only for the positive values of the x. So no negative or 0 can be tolerated in log normal distribution. So it is not possible to get that kind of thing in this distribution. So if you are getting all positive and a very low mean while large variance and all positive, so in that case then chances are high that the distribution is log normal. So how to deal with this kind of situation? So the best option is to transform this into the normal distribution, log normal to the normal distribution. Just take the logarithms. So log normal distributions are deceptive. We tend to remove the values as outliers and perform a t-test, ANOVA, etc., assuming the Gaussian. This is wrong. Easiest way to deal with this distribution is to transform each value to the log scale and then go ahead with the statistics or the tests assuming Gaussian distribution. So that is one of the easiest way to deal with this situation. So probability density function of the log normal distribution is defined by the mean, that is mu, and standard deviation, that is sigma, and this is the formula that we use to calculate the log normal distribution. But again, there are so many calculators available online that you can use it, and more than that, these kind of calculations are not at all useful in biological sciences, because in biology all we have to do is to convert. We have to find what kind of distribution is that. So if it is log normal, just normalize it by converting into the log scale, then perform the test. So that is the easiest way. I have linked one of the online calculator into the web sections of it. So all you have to do is to input all these things, then even the density function is also that the graph is also output in this calculator, so that it's pretty useful. So in summary, Gaussian distribution is followed when many random factors create variability. Random factors tend to offset each other. It is an additive distribution. It is possible to calculate probability of an event x from mean and standard deviation via standard normal distribution. A log normal distribution emerges when variation is caused by multiple sources of scatter which are multiplicative in nature. Easiest way to deal with log normal distribution is to transform each value to the log scale and go ahead with the tests assuming Gaussian distribution. Thank you so much for watching.